Hi everybody. First of all, I would like to present myself. My name is Iyad Rayane. I am application engineer at Zuken. The presentation I will be giving is entitled Advanced IC Packaging and Co-Design Solution with Zuken Design Force. The presentation will go as follow. First, I will start by market trends. Those are not the most fancy slides, but I need to do it every time, some marketing slides. Then I will describe briefly what are the common challenges in the system level design. After that, I will introduce the CR8000 design force solution proposed by Zuken, followed by a deeper look to design force and the solution we are proposing, and then describing briefly a co-design test case and move and sum up, finishing by a summary. By slides. In fact, what are the market trends? As you know, IoT, smart cars, and artificial intelligence are driving a lot of innovations in the semiconductor industry. Those segments are exercising a lot of pressure for innovation. The semiconductor market is expected to reach something like 900 billion euros. Those innovations are exercising pressure on semiconductor, but also on the whole ecosystem around semiconductor. Co-design and EDA tools are part of this ecosystem. Regarding the IC packaging, we notice the emergence of new technologies. This is driven by different needs, form factor, thermal dissipation, etc. As an example, the first iPhone introduced in 2007 used to have two wafer level packaging inside, whereas the iPhone 7 introduced in 2016 used to have 44 WLCSP. WLCSP stands for wafer level chip scaling package. Thus, more and more complex IC packaging techniques. Regarding the semiconductor, we often hear these days about end of Moore's law. Some people talk about end of Moore's law, some other say it's decelerating only. The number of transistors is still doubling each couple of years, but we notice another fact, which is the number of transistors bought for $1. We see that beyond 28 nanometer process nodes, the number of transistors is decreasing. This means the cost per function is increasing starting from 28 nanometer process node. Thus, using advanced process nodes can be expensive for medium to low volume productions. Only large volume can expect a return on investment. On the design side, the design cost is also exploding, as shown in this figure. While some of those costs are associated to additional complexity of rules at the smaller geometries, much of the cost increase is due to the increased complexity. This means a viable alternative is needed to transistor level scaling, and system level scaling is seen as an alternative for small to medium volume productions. What we mean by system level scaling is a having multi-die in the same package, what we also call SIP or system in package. Thus, co-design features and robust EDA tools to model and implement such systems are needed. That being said, now we introduce the need for system level tools for system level design. So what are the common challenges for this kind of designs? The main challenge in the system level design is the boundary between those different tools and teams. Those boundaries make it hard to do early feasibility study, because early feasibility study means we need to imply the full system at early stage. It makes it hard to manage ECO, engineering change order, because each time you need to run an ECO, we need to exchange data between the different teams and different tools, different environments. Make it hard to run pathfinding at system level, simulating the whole system, considering constraints at the system level, and also optimizing each subsystem from the whole system point of view. It is well known in systems engineering that each subsystem must be optimized by considering the whole system, not only the subsystem. As an example, let's take the engine of a Ferrari and put it in a small car, a small Fiat or a Peugeot. The engine is over-optimized, but the car will not stand the engine and will break down. This means that the full system is not optimized, even if one subsystem, which is the engine is over-optimized. Now, a brief description and introduction of to CR8000 with design force. In fact, design force is a multi-domain system design. It allows to design individual package and board, and also concurrently implement and optimize chip package and boards. It combines conventional 2D with 3D design in real time, offering fast system performance because it uses the latest user interface technology. It's one environment for high-speed design, constraint management, and simulation. We can also design to any manufacturing specs because we have the built-in DFM check and design force. It supports the latest network environment with a standalone data server, application server, or cloud. More generally, design force is a product-centric system-level design. As you can see in design force, we have interfaces to different database. We can import the native semiconductor database, which is open access, which is a standard in the chip environment and chip development. We can import the mechanical parts of the product itself while running also different kind of checks like collision check and mechanical checks, manufacturing assembly, and interface to different third-party analysis tools. This allows to implement any kind of combination for the system itself, whether system in package, board to board, package on package, and board on board, and so on. Now let's have a deeper look to system level co-design approach we propose in design. In fact, one slide can summarize all the advantages of design force. As you can see here, we have design force where we can see that all the database coming from different fabrics, the chip with open access, standard database, the package, and the board. This allows us to have a full view of the full system, hierarchical view. We can trace path through the whole system from one die pin through the package, the board, the second package, and to another die pin. Okay. This environment eliminates the boundary between different domains. It allows system feasibility study, easy communication between different design teams because there will be no need to spreadsheets or text or exchanging mail, since we can import the original database, the native database, directly in one environment, so we can see the impact of any changes in any subsystem to the whole system. It offers hierarchy structure, allowing pathfinding across the whole system. We can have the system level netlist in order to run simulation, and also it will make it easy to run ECO management. Other characteristics of design. It's a native system level 3D editing, not only viewing. So when we are in a 3D mode, 3D viewing mode, we can edit each object in the design. It's not only for viewing. Unified platform for concurrent SOC package and board design to optimize the I/O. Implement any package integration technology. A design force offers a tape-out quality and feasibility router for RDL, interposer, and substrate design. It can be used as an add-on on the existing flow, so you don't need to break your current flow. You can continue using your existing tools, but using design force for the early stage optimization of the full system, and then you can push each part of the design, each subsystem, and the different tools you are currently using. Again, it supports natively the open access, which is a standard for chip design, standard database for chip design, enabling design and intelligent exchange of pump placement and RDL routing. Design force supports both flows, top-down or bottom-up. In top-down, we start the design by the chip, whether we import the left def if something exists already in the chip, or we can start from scratch using high-level specifications of the chip and creating everything in design force. When I say everything for the chip, it's only the I/O pad ring, pumps, planning, and RDL routing. The I/O pad ring is the starting point to implement the chip. So you can then, once you have approved this floor plan from the system point of view, you can push this I/O pad ring to the chip implementation tool. Then we implement, we import the chip into the package, run the package escape routing and the package routing, and evaluate the package technology. Some key features of DesignForce. DesignForce supports standard interfaces like left-def GDS2 for chip data, ODP++, Gerber, and so on. We have different ways of creating and importing the component in your design. Whether BGF format, it's a format where we have the abstract information of your component, like size, location, and shape of each pin. It offers parameter creation, LPBC or semiconductor data using open access. We have also the package DRC features covering the most standard DRC, and also auto route to run fan in and fan out at the package level. For current chip designs with advanced process nodes, number of IOs is exploding and making it hard to assign chip to package pins. DesignForce have an auto pin assignment that respects the power domain and other design constraints. Regarding the SIP, system in package, DesignForce offers a multi-object design, making life easier for implementation, different implementation like package on package. It allows net update in case of swap, and allows to create embedded components and to create system inits to trace nets through the whole system. In the chip environment, DesignForce support the RDL, full support for the RDL routing, which is currently done using chip implementation tools, place and route tools that are really expensive tools. This support includes design rules, routing blockages, multi-layer routing, multi-port connections, and slot wire. Chip environment allows also the implementation of complex designs like SOC, fan-out wafer level packaging, package on package with memory co-design, as we show on this slide. The flow is the following: creating the chip data from specifications. The chip data in DF consists of IO padding, pumps, and RDL routing. When the chip pumps and RDL is done, we import the chip into the package, into the fan-out wafer level packaging, and using the multi-board functionality, we create the POP design. Of course, in the package environment, we run also the routing using the auto route functionality, and then with the multi-board, we create the package on package design. Regarding the flip chip, DesignForce allows the feasibility study and allows the analysis of different pump styles and pitches to optimize the choice from the whole system point of view. Not only the chip. We can use array pattern or staggered pattern for pumps, run RDL and import the two flavors into the package, and run the package feasibility to see which pattern offers the best performance for the system. Pumps design needs to consider SOC and package constraints. Currently, it's hard and time-consuming to run many iterations with data exchange using spreadsheets. Doing this in one environment, the environment proposed by DesignForce, is more effective and reduces considerably turnaround time. Also, the usage of pump tiles reduces considerably the ECO efforts. At the package side, DesignForce, as said previously, offers auto-route functionality. This feature matches the required constraints of the design, like power domain, clearance rules, differential pairs, and so on. We can also run some rules by area. This functionality enables a quick and fast feasibility study and supports both flavors, top-down and bottom-up flows for I/O optimization. DesignForce also supports an additional feature regarding the daisy chain. It creates this kind of designs from the guidelines with paired designs and connection check with multiboard. The design flow allows to search stroke path on selected parts, the generation of unique net names, and also creation of paired data to connect to daisy stitch and so on. Now, regarding the flow you can use with DesignForce. In fact, as we can see, as I have said, DesignForce can be used as an add-on on the existing flow. So you can start the let's say, the evaluation or the prototyping of the full system and the optimization of each subsystem upfront using design force. And then you can push each part in your current tool. For example, for the chip, you can evaluate different flavors of the I/O pad ring, of the bumps planning, of the RDL routing, from the full system point of view to see the impact on the package routability and the impact on the board also, on the performance of the full system. Once you agree on that, once you approve the floor plan, the I/O pad ring and the pumps, you can push this data into your current place and route tool for the chip and do it in your existing tool. The same for the package and the board. Whether once you have approved the pin assignment, the routability and the package technology, you can push that into your current tool to do it with your current flow. But for the package and the board, you can also do it in Design Force, because Design Force offers the full functionality for package and board implementation. This had been said, now I will present a co-design test case showing the advantages of using one environment, which is Design Force, for prototyping. The design case, the test bench we are using is a CPU core chiplets placed on a fan-out wafer level packaging in a scalable manner. Each chiplet size is 2.5 by 2.5 millimeter. One chip has 8 interface blocks. The size of the interface block is 0.45 millimeter by 0.6 millimeter. The flow is as follows. In the chip environment, we start by creating the tile pump cell, placing I/O cells, placing and assigning the pumps, and running the RDL routing. We can do different flavors for the tile pump cells in order to see the impact of different orientations of the pump cell and of the tile cells. Once we have done that, we import those chiplets into the package in the SIP system and package environment. We run the routing, die to die, die to ball, and the power planning. Then, after creating critical signal routing, the electrical characteristics can be checked during the design with the embedded simulators, power integration and power integrity and signal integrity simulators built in Design Force, or also we can output a SPICE netlist for third-party tools and for further analysis. At the chiplet side, in the chip environment, we have created the first tile pump cell having 3x4 pumps, and created a first chiplet using this tile cell. The second one is 4x3 tile pump cell and the corresponding chiplet. As you can see, in this case, we have the length of the RDL routing is shorter than this case. On the SIP side, on the package side, we have created several prototypes of the SIP designs. The first case using the 3x4 pump tile cell. The case 1 with 4x3 pump tile cell. Case 3 with the 4x3, but we have reduced the spacing between the chiplets. And in case 4, we have used a chiplet bridge layer. To evaluate and compare performance of the 4 SIP designs, we use some factors such as track length and latency. In the case number 2, as pump depth was reduced, the escape routing length was shortened and the route length between chiplets was equalized. The analysis using built-in simulators confirmed that the delay variation was smaller in all cases compared to case number 1. In this test case, we see that the case number 4, the SIP floor plan number 4, was the most performant optimized one. Thus, Design Force helped for a quick decision for system and package implementation. It helped in deciding what tile pump cells we need to use in the chip level and what kind of floor plan we need to use to do at the package side in order to implement the system and package. It's helped to select the best chip I/O and pumps planning and the best floor plan for the SIP. So in one environment, we could really run the optimization and the full system and see the impact of each modification at the chip side or at the package side on the full system performance. Let's finish by the summary. Design Force is a system-level co-design tool allowing the optimization of each subsystem from the system-level point of view. It's a native 3D product-centric platform with dedicated TRCs that shortens design cycle times and improves design quality. It reduces software cost by minimizing the need for IC layout tools to conduct co-design. Some of the features at the chip side can be done using Design Force, rather than using IC layout tools, place and route tools that are really expensive tools. Eliminate manual data exchange between SOC package and board with a unified co-design environment. Optimizes IOs across domains through hierarchical design environment. Conduct feasibility and implementation of any package integration technology, intelligently design and exchange chip and pump placement and RDA routing. And finally, offers tight collaboration with upfront analysis tools to ensure high performance and early detection of signal quality issues. Thank you for your attention. For your questions. Thanks.